This is step 1 support assignment number 3. It's actually a step 1 question from 2004, question number 2, in case you want to look it up. Here's the question. You can do it before I do. It's actually a really nice question. We'll start with part 1, obviously. It's talking about this new function that you may have never seen before called the square bracket notation. It means the greatest integer less than or equal to x, no matter what x is. So for example, square bracket of pi is 3, square bracket of root 24. Now we know root 24 is just less than 5 because root 25 is 5. Is 4, and then square bracket of 5 is 5. Basically, it just rounds the number down if the number is some kind of decimal between two numbers. So 3.14 rounds down to 3. 5.8, whatever this is, rounds down to 4. 5 just stays the same as 5. So it just rounds it down. You may have encountered this function before. It's called the floor function more normally. The floor function because it literally pushes the number down to the floor, like to the lowest nearest integer. So if I ever refer to it as the floor function during this video, just because that's how I'm familiar with it, that's what I mean. It's the floor function is essentially what this is normally called. But anyway, sketch the graph of this root square bracket function or floor function. Well, we'll do that bit first, and then we'll deal with this. Let's sketch it first. Now, to sketch, obviously we're going to put some axis down, and we'll label some things down as well. Now, all I'm going to do is I'm actually just going to plot this, because I have no idea what it might look like. I've never plotted something like this before, so I'm not going to sketch it. I'm just going to plot it and see what happens. So, okay, well, what happens when x is, say, 1? Well, the square bracket of 1 is just 1. So, I should also say I'm actually going to start out just by plotting this, and then I'll deal with the root of it. Let's plot this because it's more simple. But square bracket of 1 is just 1. Now, square bracket of a half rounds down to the nearest integer is 0. So square bracket of a half is just 0. And square bracket of anything between 0 and 1 is just 0, because all those numbers get squashed down into 0. And now, the square bracket of like 1.5, that's going to also be 1. It gets rounded down to 1. And so anything between 1 and 2 gets rounded down to 1. 2 will just become 2, but then anything in between 2 and 3 stays being 2, because it gets rounded down to 2 as well. And then 3 becomes 3, and so on. So you end up drawing this kind of stepped function here. This is the function y equals square bracket x, where anything in between two integers just gets rounded down to the next lowest integer, and then you just jump up to the next step and jump up to the next step. Notice I haven't connected these steps, and the reason for that is that there's nothing that would actually go in those, if I were to draw a line from here to here, there's nothing that actually goes there. Like there's no coordinate that actually exists here, because you never get a y output of like 1.5. Your y outputs are always integers, because you always round down to the next nearest integer. So that's why I haven't connected these steps up. Now that I've drawn that, I can start considering what this graph actually does look like. And now all I need to do is do the square root to each of these steps. So the square root of this line, well, square root of 0 is just 0. The square root of the 1 line stays at 1. And now, if I'm at 2 and I square root it, I go down to about 1.4. And if I'm at 3, so I used to be at 3 anywhere here, but when I square root that, I jump down to 1.7 or so. And if I'm at here, now these numbers like 4.5 used to round down to 4, but when I square root that, I push that down to 2, because the square root of 4 is obviously 2, and that's going to roughly be the root of the square bracket function of x. Stepping up by a smaller and smaller amount each time, actually, is how it works. Okay, now show that the integral of the root of the square bracket of x is equal to this thing. Now, I have no idea how to square roots, or how to integrate, I should say, these floor functions or square bracket functions, certainly not the roots of them either. So I'm obviously not going to do this integral, but I'm going to think about what the integral represents. And we should know that the integral represents the area underneath the graph between two limits. And when you look at this graph, what's nice about this graph is that we think, well, actually, its area is just made up of a ton of rectangles, right? So I could work out the area of this without integrating. The area underneath this graph is just this rectangle, which is height 1, width 1, so area 1, plus this rectangle, which is width 1, height root 2, remember, so area root 2, plus this rectangle, which is height root 3, width 1, and so on. And I'm going to do that all the way until I get to a. Now, a is a positive integer. So if a is some integer on here, the rectangle before it ends on a, because a is an integer. And what's the area of that rectangle? Well, look here, this area is root 5 and it ends on a 6. This is root 4, ends on a 5. So this area is root a minus 1, just looking at the pattern. Right? And so all I need to do to work out the integral of this is add up all of these rectangles. So add up 1 plus root 2, this is maybe a root 1 you could say, plus root 3, plus root 4, plus root 5, all the way until there. Notice how I wrote root 4 as root 4. I could have said it's 2 times 1, but I wrote it as root 4 to maintain the pattern here. Okay, well, if you're just adding up a load of roots, root 1 plus root 2 plus root 3 all the way to root a minus 1, that's by definition just this. We can start at r is 0 because root 0 is just nothing, so that's almost like having a 0 here. And then you go root 1 plus root 2 plus root 3 plus root 4 all the way up to the end. And so we've got our answer here. Part 2 is quite interesting because it's showing a similar thing. You're showing the integral is equal to this new kind of expression, just like this thing. But notice what they haven't asked us to do. They haven't asked us to sketch it. And that's not because they don't want you to sketch it, that's testing this idea in step whereby you always want to take ideas that they've given you before, they just might not tell you to do that directly. So just because they haven't told us to sketch it, I think it would be a really good idea to sketch it still, because that will still enable us to answer this very similar question that we've got here. So let's sketch this graph first. So let's sketch y equals 2 to the power, the square brackets of x is what I'm going to try and sketch here. Now again, to do that, I'm just going to try and plot some points. So what happens to the point 0.5? Put 0.5 in there, that obviously rounds down to 0, but 2 to the power 0 is 1. So actually our first kind of step, and maybe we can guess that this is still like a stepped function. The first step is at 1, because anything between 0 and 1 is going to do this exact thing. 0.1 is going to go to the 0, 0.9 is going to go to 0, and you still get that. So our first step is there. Now, what if we're between 1 and 2? Well, 1.5, say, and that rounds down to 1. Which then 2 to the power 1 is just 2. So that's on our next step. And again, anything between 1 and 2 is going to do exactly that, right? So we're going to be on that step. Between 2 and 3, put in 2.5, well, that rounds down to 2, and then you get 2 squared, which is 4. And so we're up a step here. And here, this pattern is going to continue, right? This is, the steps are going to get further and further apart, because here you got like a 3.5, that rounds down to 3, and then you'll be doing 2 to the power 3, which is 8. So if I just draw the graph a little bit bigger, we're going to go up to 8, and then the next one will be 2 to the power 4, which is 16, and the steps are going to increase in distance across exponentially, like so. Okay, so now that we've sketched the function, yep, that's the sketch. Obviously it continues longer, but I can't bother to draw it longer yet. We're now showing this integral here, and again, I'm not going to integrate this, I'm just going to look at the area. I'm going to say the integral of this is just area, that's what integrals are in some respect. So if I could work out the areas underneath these, and they're still just rectangles, then I could work that out. So this is just 1 times 1, which is just 1. This is 1 times 2, which is area 2. This is 1 times 4, which is area 4. And this is 1 times 8, which is area 8. So you can probably see a pattern here. And now I'm going up to a, again, where a is a positive integer. So there's something a here. It's a positive integer, so the rectangle ends at a, just like this rectangle ends at 4. And now how tall is this rectangle here? Well, notice here, this here, I could write as 2 to the power 1. This is 2 to the power 2, and this is 2 to the power 3. And so the power is 1 less than the number that you end on, or it's the same as the number before it. So this power here, this is going to be a 2 to the power, and it's 2 to the power a minus 1, just following the pattern. 3 to a 4, 2 to the 3, 1 to the 2. This is, I guess, 2 to the power 0, so 0 to a 1. So this is 1 less than the thing you end up at. And so the integral is just all of these rectangles added up together, which is 1 plus 2 plus 4 plus 8 plus to this last thing. Now that isn't the expression they've given us, but we can figure that out, right? Because what do you have to do to get from term to term? Well, you just times by 2, right? Times by 2, times by 2, times by 2 to get an 8. The next one would have been 16. So this is a geometric series of starting term 1, ratio 2, timesing by 2 each time. And how many terms are there here? Take a second to think about it. Perhaps the easiest way to count how many terms there are is to look back at this picture, because as you arrive at 3, you have 3 rectangles. As you arrive at 4, you have 4 rectangles to count. As you arrive at 8, you'll have a rectangles to count. So 2 rectangles to count if you integrate up to 2, 3 if you integrate up to 3, 4 rectangles up to 4, a rectangles up to a. So there's going to be a of these terms to add together, if you see that. And so, okay, well, we have starting term 1, ratio 2, a terms. This is the formula for the sum of geometric series. This a has nothing to do with this a, unfortunately. This is the starting term. So our starting term is 1, our ratio is 2, and our n is a, confusingly. So our integral is going to be 1 into 2 to the power a minus 1 over 2 minus 1. That's obviously just 1, that's just 1, and so this just simplifies to that, which is what they asked. Okay, very nice. Part 3. Determine exactly the same thing, but this time a is positive but not an integer. Okay, so we draw the same graph. Right, this is the same graph I drew before. And I'm still talking about those rectangles, area 1, area 2, area 3, area 4, sorry, area 8. But now when I go all the way over here, this a isn't an integer. So a rectangle doesn't end on it. The place where the nearest rectangle ends is at the floor function or the square bracket function of a. That's where the rectangle ends. So imagine a is like 8.3. The nearest rectangle ends at 8, right? So this is going to be a rectangle near it. So I can do these rectangles that I did before, right? So this area, this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3, which means this area here is going to be 2 to the power floor function of a minus 1, because again, you've got those, you've got that pattern of being 1 less than the thing you end on. So we're 1 less than the thing we end on. So we're 1 less than the floor function of a. Okay, so that's fine. Now I can add up all those rectangles, but I still have a little bit of area to go because the next rectangle is going to be thicker than this. Like the next rectangle is the same width as they all are, but I'm going to end it at a, right? Because I'm only integrating up to a. Now, how tall is this rectangle? Well, it's 2 to the power floor function of a tall, because if this is 2 to the power floor function of a minus 1, the next one, again, the powers are just increasing by 1. So that's how tall this one is. So this is 2 to the power 3 tall, this is 2 to the power 2 tall, this is 2 to the power 1 tall, this is 2 to the power a floor function tall. And how wide is it? Well, it's this wide, which is a minus the floor function of a. So the area of this last little rectangle we want to add in is, it's not really little, but it's 2 to the floor function of a times the width. It's height times width, right? Which is a minus the floor function of a. So the total area, which is to say this integral is going to be equal to the total area, which is 1 plus 2 plus 4 plus 8, all the way up to 2 to the power this. And then we also add in the thinner rectangle on the end. And you get almost all the marks for that, but this does actually simplify, because these first few terms that we saw, in the same way that if a were an integer, these things add up to that. That was in part B, remember? If a isn't an integer, then this thing is, like the floor function is always an integer, or the square bracket function, whatever you want to call it, is always an integer. So we can just replace this theory with that, right? So if a is not an integer, we can just do this thing here, because now we're rounding down to make it so. Right, so this just works. And so we can replace that with this. So that bit there has just become this bit here. There's not really much we can do with this anymore. I guess I could maybe do some factorizing of this 2 to the floor function a, but it doesn't really matter. I think this is good enough. And that's my final answer.